Welcome to spectroscopy, everyone. This is one of the harder parts of analytic chemistry and of organic chemistry. Unfortunately, we don't have the equipment to perform any of these experiments, but you need to learn how to do the measurements and do the experiments. Read the data in order to answer questions for the AP and IB exams. So, here we go. The first one is the mass spectrometer, which you have already learned about in Chem 1. You learned about how different isotopes are read and their percent abundances. In organic chemistry, what we do, instead of sending in just one element into the mass spectrometer, we send in an entire molecule. Now, with an element, it breaks it up into the different isotopes, the different masses, and we detect their percent abundances. In the case of organic molecules, it fragments a molecule. So if you imagine a long chain of hydrocarbon, it actually breaks it up into pieces and chunks, and that's what you're measuring, is you're measuring the abundance of each one of those fragments of the molecule that's been broken up or fragmented. The mass spectrometer, you should remember how it works. The sample goes in here at the beginning. It is ionized, so it ends up with a charge. It is then, accelerated through this part, and here there's a big magnet. The magnet is what deflects it, so that the things that are more heavy are deflected less, and the things that are less heavy are deflected more. And then on the end over here, there's a detector that detects, how much of the original sample comes through, and therefore how much has a particular mass, in this case of an isotope, or how much has a particular fragment. And we'll take a look at this data here in just a minute. The other part on this slide up here is the index of hydrogen deficiency. When I first started teaching IB chemistry, this confused me a lot, because I had never heard of it before. It turns out it's the degree of saturation, which makes a lot more sense, and that is something that I recognized from college. But it basically is a calculation on how many places there were hydrogens missing from the carbons. So you do this little calculation. There's this little formula. It's 2 times the number of carbons plus 2 plus nitrogen. Usually we don't deal with things that have nitrogen. Minus X. X represents any halogen. Minus hydrogen. And then all of that divided by 2. And you get this number, and it tells you the index of hydrogen deficiency. If you get a number that is 0, or relatively low, sometimes you get like a half, which is weird, but not most of the time. It's usually a whole number. If you get something that's 0, then it's completely saturated. If you get a number that is 1, then it has 1 degree of unsaturation, which means it has 1 double bond. If you have 2, it means you either have a triple bond or 2 double bonds, etc., etc. It's one piece of the puzzle when we're looking at how a molecule is constructed. So back to the mass spectrometer. Our next slide here takes a look at the different fragments. Now, you should get a handout that has this table on it. These are just some common different fragments and their masses. I often find them a little bit more confusing than anything else, but it does help some people. This line here represents the mass of the fragment if all you do is you take the molecule and knock off an electron to make it a positively charged ion. So this top number is actually the entire molecule. So the molecular mass here is 98. And then we have other fragments, 83, 55, 43, 39, and 29. Now there are other little things coming along here, and those are other different isotopes. Again, when you take an analytic chemistry class in college, they will go over a lot of these in more detail. But these are little fragments that are less common and definitely less important to what you're doing for this class. So since we have a fragment that's 83, we know that somehow if we take something off of this, it's going to have a mass of 83. My guess is that we're going to remove a CH3 off of here, because then that would remove 15 from its mass, and so instead of having a mass of 98, it would have a mass of only 90 or only 83, and that would be the difference. 55, again, you could figure out where to break this so that the mass of what you have left is 55. 43 is not on this table, although it's a pretty common fragment. 29, there are a couple different fragments. You could have CH3, or you could have CHO. You're not going to have CHO from this because it's not going to break in two places. It's not going to break here and here. It's only going to break in one place at a time. So my guess is that, you know, the CH3 is probably more common, something fragmenting over here. It's not an exact science, and you kind of have to use it as clues to figure out what the entire molecule was. The most helpful piece of information is actually this top number, because it tells us the mass of the entire molecule. And molecular mass, if we know the formula mass, or empirical mass, and we know the molecular mass, we can figure out the molecular formula, and that's really very helpful in trying to then figure out what the structure of the molecule is. I hope this helps a little bit, and I hope it helps you understand the spectrometry videos that you're watching on OChem. Again, please email me with questions, and I'll try to help as much as possible.